I want you to picture a scenario. It's a Friday afternoon. You're staring at your screen, and you have just pushed what is objectively a tiny, microscopic, seemingly harmless code update.
Oh no, the classic Friday deploy.
Right, the absolute worst idea. But we're talking like maybe 3 lines of code, a minor bug fix in some random microservice.
hmm
You hit deploy, you lean back, take a sip of coffee, and suddenly,
Everything catches on fire.
literally everything.
Yeah.
All the monitoring dashboards on your second monitor just turn crimson red. The Slack notifications start pinging frantically. PagerDuty is going off. The entire application has just come crashing down.
Yeah, that is a universally dreaded feeling.
It really is stomach-dropping.
Uh,
Have you ever been there? Because 9 times out of 10, the culprit behind that specific kind of meltdown is a failing API.
it's a terrifying moment. And the reality is, I mean, it happens to the best engineering teams in the world. APIs are basically the connective tissue of modern architecture.
The glue holding it all together.
Exactly. They're handling the authentication, the database queries, all the third-party integrations. So when a single strand of that tissue tears, you don't just lose like one feature. You often experience this massive cascading failure across the entire system.
Which is exactly why we are diving into a really fascinating breakdown today. We have a source called The Architect's Guide to 9 Essential API Testing Pillars.
Yeah.
And the core argument here is that, well, hoping your APIs work in production is just not a strategy.
No hope is definitely not a deployment strategy.
Definitely not. You need an automated, rigorous system. So the mission for this deep dive is to really unpack these 9 structural pillars of testing. The goal is so that you can build truly bulletproof, scalable, and secure CI/CD pipelines.
Which is so critical today.
Absolutely. Okay, let's unpack this. When we are staring at a massive, incredibly complex application, where do we even begin validating it without getting just completely overwhelmed?
Well, you have to start at the absolute foundation, which the source identifies as smoke testing.
Smoke testing. Okay.
Yeah. Yeah, because before you run these massive suites of complex algorithms, before you check for, security vulnerabilities or database latency, you just need to know if the deployment actually worked.
Like, is the thing even turned on?
Exactly. Is the environment alive?
Yeah.
Smoke testing is your absolute baseline sanity check.
I always think of it like building a brand new house. When the electrician finishes wiring the entire place, their very first step isn't to walk around and meticulously plug a voltage meter into like every single wall outlet in Meth's bedroom to check for optimal impedance.
Right, that would take forever.
Yeah. Folks, they just go down to the basement, flip the main breaker, and stand back to see if the lights turn on. Or, if the walls literally start smoking.
That is the perfect analogy. Because if the walls are smoking, there is absolutely no point in testing the individual outlets. You have a fundamental system failure.
Right, the house is on fire.
Yeah. So in a CI/CD pipeline, the smoke test is designed to fail fast. You send a basic, super lightweight request to the API just to see if you get a 200 OK response back.
Just a simple ping.
Exactly. Are the servers awake? Did the containers spin up correctly? If the smoke test fails, the build halts immediately. You don't waste 45 minutes running a massive testing suite on an environment that's already broken.
Okay, so let's say the breaker didn't trip. The smoke is cleared, the infrastructure is awake, and those basic HTTP requests are returning successfully. But just because the lights are on doesn't mean the house is actually livable, right? The APIs are responding, but are they giving us the right answers?
And that is exactly where we transition to the second pillar, which is functional testing. We move from that simple pulse check to strict logic validation.
So getting into the weeds a bit more.
Yeah. You take the actual functional specifications, so the contract or the open API spec of what that software is actually supposed to do, and you feed exact deterministic input data into the API. Then you carefully capture the response payload to see if the actual result matches your mathematically expected result.
Got it. So if I have, say, a billing API that calculates prorated subscription upgrades, a functional test means I send it a really highly specific scenario.
Right, like a specific user state.
Yeah, like a user upgrading exactly midway through the 30-day billing cycle. And then I explicitly check the JSON response to make sure the calculated prorated charge is precisely, $12.50.
Yes. And what's fascinating here is the isolation aspect of it. Functional testing requires you to treat that specific API endpoint in a total vacuum.
Okay, a vacuum, meaning ignoring the rest of the app.
Exactly.
Oh.
You are isolating the core business logic. Does the internal math work? Does it handle null values correctly? Does it throw the proper, 400 bad request error if you send a date format it just doesn't recognize.
Proving the structural integrity of the individual brick.
Yes, before you ever try to build a wall with it.
But I mean, modern software isn't just a pile of isolated bricks.
Yeah.
A microservice rarely exists in a vacuum in the real world.
Very true.
Once we know the individual endpoints work perfectly on their own, we have to see what happens when they actually start talking to each other. Because an isolated calculator might work beautifully, but if it has to hand off its math to a database service that speaks a totally different language, the whole thing just falls apart.
Which brings us directly to integration testing. This is where architectural complexity really rears its head. In an integration test, we're no longer testing the individual brick. We are testing the mortar between them.
The connections.
Right. We intentionally follow a test plan that chains several different API calls together across completely different services.
I always imagine it like an air traffic controller coordinating planes from completely different airlines. Each plane flies perfectly on its own. That is our functional test.
I like that.
But the integration test is making sure that when plane A from, say, the billing service needs to land on the runway, controlled by the notification service, they are speaking the exact same language and using the same protocols. The catastrophe usually doesn't happen in the air, it happens during the handoff.
And those handoffs are notoriously fragile. Think about it. Let's say your user creation API passes its data to your welcome email API.
Happens all the time.
Right. Now, if the creation API formats the user's birth date as a string, but the email API has recently been updated to expect a UNIX timestamp integer.
Oh, the email API is going to panic.
It will panic and throw an exception immediately. And the crazy thing is, both of those APIs pass their functional tests in isolation.
Right. But together, they just crash.
Exactly. So integration testing verifies that the data serialization, the schema validation, and the actual communication protocols between the services are just perfectly aligned.
Okay, so we're checking the handoffs. But code is never static, right? We are constantly adding new features, we're tweaking the logic, optimizing the database queries. What happens when we introduce brand new code into this finely tuned machine?
Well, that's the big question.
Right. The source material highlights a really critical pillar for this, which is regression testing. It basically exists to save you from your own updates.
Yeah, regression testing is really the safety net for evolving systems. When you merge new code, you run your comprehensive suite of historical tests against the new build.
Using old data.
Yes. You use the exact same input data you have always used, and you ensure the system still produces the exact same output. You are proving that your new shiny code didn't silently break an existing, completely unrelated behavior somewhere else.
Okay, let me push back on this for a second, because I hear developers complain about this all the time. If I just spent 3 grueling weeks building this really innovative new feature, let's say a complex AI recommendation engine for an e-commerce platform,
Sure.
why am I wasting valuable pipeline compute time feeding it legacy inputs from 2 years ago? Shouldn't my testing focus entirely on the new logic I just wrote?
Well, if we connect this to the bigger picture, innovation is a net negative if it destroys your foundation.
Oh, that's a good way to put it.
Right. Imagine you update your API to support that new AI recommendation engine. Brilliant. But in doing so, a developer accidentally alters a shared utility function, which then silently breaks the standard shopping cart's ability to calculate shipping taxes.
Oh, wow. Yeah, that's disaster.
You haven't progressed at all. You've just introduced catastrophic technical debt. So regression testing isn't just about testing the code itself. It is about testing your assumptions. It proves that you haven't accidentally resurrected zombie bugs that you supposedly killed 3 versions ago.
It's the ultimate defense against collateral damage. I really like that.
Yeah.
Okay, let's take stock for a second. We've checked the pulse with the smoke test.
Yep.
We've validated the isolated math with functional tests. We've watched the APIs seamlessly hand off data in the integration tests. And we've proven our new updates aren't sabotaging the old architecture through regression tests.
A very solid foundation.
Right. The logic is flawless. The contracts hold. But functional perfection is entirely theoretical until real, completely unpredictable humans show up to actually use it. We have to transition our thinking from pure logic to physical performance.
You really do, because a system behaves very differently under load. An API might execute a database query in, say, 10 milliseconds when just one developer is testing it locally on their laptop.
Sure, lightning fast.
But what happens when 5,000 concurrent users hit that exact same endpoint at the exact same millisecond? Memory fills up, thread pools get exhausted, and that is exactly where load testing becomes critical.
Right. And the source mentions leveraging tools like Apache JMeter for this, right?
Yeah, tools like JMeter or Gatling, they allow you to spin up these massive distributed test engines that artificially simulate concurrent user traffic. But the keyword for load testing is expected traffic.
Expected. Okay.
You are establishing a performance baseline under anticipated conditions. So if your analytics show you normally get 1,000 checkouts an hour on a Tuesday morning, you configure your load test to simulate 1,000 checkouts an hour. You're just verifying that the API responds efficiently without any crazy latency spikes under standard operational weight.
It's like prepping a restaurant kitchen for a standard Friday night dinner rush. You know every table is going to be full, the general cadence of the appetizer and entree orders.
Right, it's busy but predictable.
Exactly. And you just want to verify that the chefs can handle that expected, consistent capacity without falling behind or, burning the steaks.
But then we had the flip side of that coin, which is stress testing. And here, we throw expected completely out the window.
Uh-oh.
Yeah, we aren't testing the normal Friday dinner rush anymore.
Sticking with the restaurant analogy, stress testing is like dumping 50 busloads of extremely hungry, really aggressive tourists into the lobby, all at the exact same second, demanding food just to see if the kitchen literally catches on fire.
That is exactly what it is. You are deliberately pushing the system way past its documented architectural limits. You blast the API with extreme spikes in traffic until it breaks.
Until it breaks. So failure is the goal.
Yes. But, and this is a really vital mechanism to understand, the goal of stress testing isn't just to point and laugh when the server inevitably goes down. The system will break. The actual engineering value is observing exactly how it fails.
Wait, why does the how matter? I mean, if the user gets an error screen, broken is broken, right?
Well, architecturally, there is a massive difference between a controlled failure and a catastrophic failure. Like, does your system gracefully shed load?
What do you mean by shed load?
For instance, if the traffic spikes 10,000%, a robust API will trigger what's called a circuit breaker pattern. It will quickly return a 503 service unavailable response to the user, perhaps suggesting they try again in a few minutes. That is a graceful degradation.
I see. It protects the underlying infrastructure from melting down.
Exactly. A poorly designed system, on the other hand, won't shed the load. It'll try to process every single request at once. The thread pool exhausts, the server runs out of RAM, it crashes mid-process, and suddenly, boom, you have corrupted the transactional database.
Oh, man. That's a nightmare.
It is. Stress testing forces you to design bulkheads into your software, just like a submarine. If one compartment floods, you seal it off so the whole ship doesn't sink.
Wow. Graceful failure as an actual architectural design goal. That is a massive paradigm shift.
Oh.
Okay, moving down the pipeline. Knowing the system won't physically melt under a flash sale traffic spike is fantastic.
Okay.
But a robust infrastructure still needs to be defended from malicious actors, right?
Well, absolutely.
While somehow simultaneously remaining perfectly accessible for the actual customer. It's like we are constantly balancing this heavy iron shield with a friendly welcome mat.
Which brings us into the threat landscape with security testing. Modern CI/CD pipelines require you to really shift left with security, meaning you test for vulnerabilities long before the code ever hits production.
Catch it early.
Exactly. You are testing your endpoints against strict security specifications. Like, are the APIs properly enforcing OAuth or JWT authentication? Is sensitive payload data actually encrypted both in transit and at rest?
Because APIs are essentially just invisible, programmatic doors into your internal databases. You have to make sure that deadbolts actually work against someone actively trying to pick the lock.
And hackers aren't just trying to pick the lock, they're trying to trick the door into opening itself.
Right.
Security testing automatically scans for things like SQL injection attacks, where a malicious user tries to pass database commands right through an API input field, or cross-site scripting vulnerabilities. The mission is to systematically attack your own system.
Mimicking the bad guys.
Yeah, mimicking the behavior of a bad actor to uncover exposed endpoints before they can be exploited out in the wild.
And while you are busy locking down those invisible back-end doors, you also have to make sure the actual visible front of the house works for the person who actually wants to buy your product. Which leads us to the 8th pillar, UI testing, user interface.
Yep, the front end.
Now, here's where it gets really interesting. Some engineers might look at an architect's guide to API testing and wonder why UI testing is even included. I mean, APIs are back-end, UI is front-end. They seem totally separate.
They do seem separate, but in a modern single-page application, they are hopelessly intertwined. The API is the invisible engine, but the UI is the steering wheel.
I don't like that.
You cannot validate the driver's experience without testing how the steering wheel actually connects to the engine.
So we aren't just testing if a button is, like, the right shade of blue or if the CSS layout looks pretty on a mobile screen. We're actually testing the payload generation.
Precisely. When a user fills out a complex form and clicks the Submit Order button on the screen, does the JavaScript running in the browser actually assemble and serialize the correct JSON payload to send to the API?
Right. Does it send the right data format?
And, just as importantly, we have to test the return trip. When the API successfully processes that order and sends a 201 created message back, does the UI properly parse that response and render a nice green check mark for the user? Or does it fail silently and leave them staring at a blank screen?
It really bridges the gap because you could have a perfectly engineered, mathematically flawless backend API, right? But if the front-end client formats the data backward before sending it, or just doesn't know how to read the success message.
The app is still broken.
Exactly. The human being holding the phone still experiences a totally broken app. UI testing validates that entire complex round trip from the user's thumb tap through the internet down into your database and back up to their eyeballs.
It ensures the technical contract translates into actual user value.
Okay, we are in the home stretch here. Let's look at what we've accomplished. We have tested expected use. We have tested heavy aggressive use. We have simulated known hacker behaviors, and we've validated human button clicks.
We've covered a lot of ground.
We have meticulously followed the rules of software architecture. But what happens when we abandon all the rules entirely? What happens when we introduce absolute, unadulterated nonsense into the pipeline?
That brings us to our final structural pillar, fuzz testing. And as the source material aptly describes it, this is pure chaos engineering.
Pure chaos. So instead of feeding the API clean expected JSON data or even known malicious SQL injections, you deliberately bombard the system with massive amounts of random, totally invalid mutated data.
You are injecting garbage. Pure garbage. If an API endpoint expects a standard 5-digit zip code, you send it a 10-megabyte file of random Cyrillic characters. You send it emojis, you send it a negative billion, you send it null values wrapped in infinitely nested arrays.
Just to see what happens. But
Yeah.
practically speaking, why bother? Like, why feed a system literal garbage when real users are supposed to be interacting with specifically designed front-end UI forms that strictly restrict what they can even type in? If I have a drop-down menu that only allows state abbreviations, why would an architect spend time testing what happens if someone magically shoves the entire text of OBDict into that backend field?
Well, this raises an important question about the massive difference between what the front end allows and what the back end receives. You cannot rely on front-end UI restrictions to protect your back-end APIs.
Because they can be bypassed.
Exactly. Once an endpoint is publicly exposed to the internet, anyone can bypass your pretty UI and send HTTP requests directly to it via the command line. The goal of fuzz testing is to uncover hidden memory leaks, buffer overflows, or backdoor unhandled exceptions that only trigger when the system is forced to process the unpredictable.
But how does sending Moby Dick to a zip code field actually cause a memory leak?
It comes down to how the application allocates its resources. If the API logic assumes the zip code will never be long